Welcome back, everybody. Today we're going to be doing our first set of multiple choice questions. Let's get into it. So, first question, at which location is the magnitude of the force on the block in a spring block system a maximum? Okay, so we're looking for the maximum force. So we should know when it is at this equilibrium position here, the spring isn't stretched or compressed, so there's no real force onto this. I should say there's no force of the spring onto it, okay? There's a normal force in gravity, but the net force is zero. We should know that when it's at its amplitude, whether it's a negative amplitude or positive amplitude, that's where it's stretched and compressed the most. So that's when the force of the spring will be the most. And this is also where the acceleration is the most, when it's at the amplitude or the negative amplitude. So D is going to be our correct answer. Let's move on. Number 2, at which location is the magnitude of the force on the block in a spring block system a minimum? So we just talked about this, but we should know it's at a minimum when it's at its equilibrium position, because again, the spring is not compressed or stretched. So when it's at its equilibrium, the position is equal to 0. That is when the net force is equal to 0 as well. We should know at this point, even though it has 0 acceleration and 0 force, or I should say the net force is 0, what I should say is it is having the maximum velocity. This is where it's going the fastest. Okay, so this is where it's going the fastest because at the amplitude it's going the slowest with the velocity of 0 because it comes to a stop and gets faster and faster and faster until it reaches the equilibrium position. Once it passes it, it starts to slow down. Okay, moving on. Which of the following graphs describes simple periodic motion with amplitude 2 centimeters and angular frequency 2 radians per second? Okay, looking at this right away, we can get rid of D and E. We can get rid of D and E because we can see the amplitude for both D and E is actually 1 centimeter, and A, B, and C is all 2 centimeters. Okay, but how are we going to find angular frequency equal to 2 radians per second? So we should know angular frequency is equal to 2 pi divided by t. So if angular frequency is 2, and this is going to be equal to 2 pi divided by t, what we can see is t is equal to pi. So this is going to be equal to around 3.14. So we can look in the graph here, which one is around 3.14. This one has a period around 2, so that's not it. This one has a period around, seems like 3 point something, so this looks like it's going to be it. Okay? Let's move on. Example number 4. A mass m is attached to an ideal massless spring. When this system is set in motion with amplitude a, it has a period t. What is a period if the amplitude of the motion is increased to 2a? So how we want to look at problems like this, maybe you want to draw a picture of this. But what we have here, let's say this is the equilibrium position, and this is 2a. And then we have another equilibrium position. Let's say it's not stretched as much. Let's say that this is a, it's oscillating back and forth like this. And we're trying to find the period. What we should primarily be doing is we should be looking at the formula. We see the formula is 2 pi square root of m over k. Knowing this, we can see that amplitude isn't in the formula. And if it's not in the formula, that means it's going to have no effect. If it has no effect, that means the period is going to be the same, whether this is 2a, 10a, or just a. Okay? Number 5. If we double only the amplitude of a vibrating ideal massless spring and the mechanical energy of the system increases by a factor of square root of 2, increases by a factor of 2, increases by a factor of 3, increases by a factor of 4, no change. Okay. So again, what we're doing is we're doubling the amplitude. So we should think about energy. So energy, in this chapter, we're mostly talking about kinetic energy and elastic potential energy. What we should know is the elastic potential energy is 1/2 kx squared. So if this x changes by a factor of 2, because the amplitude is going to change by a factor of 2, this will be 2x squared, meaning this side of the equation increases by a factor of 4, meaning this side of the equation is going to increase by a factor of 4. So that means the total energy also is going to increase by a factor of 4 here. Okay, because when it's at its amplitude, it's all elastic potential energy. If the amplitude doubles, that means the energy increases by a factor of 4. Okay, moving on. If a mass m is attached to an ideal massless spring, when this spring is set in motion, it has a period t. What is the period if the mass is doubled to 2m? Again, you could draw a picture if you want, but more importantly, we want to look at the equation we're going to be using for this. So try to think of what equation we'll be using. And we're going to look at this main one. And we're going to notice, okay, we're going to change the mass by a factor of 2. So this changes by a factor of 2, meaning this side of the equation increases by a factor of 2. Meaning this side of the equation has to also increase by a factor of 2, giving us the answer as C as our final answer. Okay? And that's it for multiple choice, guys. Thanks for watching. Next time we'll be talking about pendulums, simple pendulums.